In the last few videos, we've learned how to find eigenvalues, eigenvectors, and eigenspaces. And we've seen several examples of both 2 by 2 and 3 by 3 matrices. We've seen examples where we got sort of distinct eigenvalues, repeated eigenvalues, and complex or imaginary eigenvalues. In particular, the case of the repeated eigenvalues, we did not always have sort of the same general behavior of the eigenvectors. In this video, we're going to be sort of taking all of that and looking at this question. If A is an n by n matrix, can we form a basis of Rn consisting of eigenvectors of A? So again, we did those examples in the last few videos. There were 6 of them total. The first 3 were 2 by 2 matrices, and then we had 3 by 3 matrices. And you can see the results here. If you haven't seen those videos, I definitely recommend going back and taking a look. We go through all the work of for the 2 by 2 case, finding those characteristic polynomials and eigenvalues. For the 3 by 3, we mostly use the computer to help us out. But you can go back and see like the original matrices we used and how we landed on those. But for this video, I want to just sort of focus on the form, and we'll come back to this idea specifically for the repeated cases, as those are going to be the most interesting ones, the repeated eigenvalues, I should say. So the multiplicity of an eigenvalue, if A is an n by n matrix, then the determinant of A minus lambda I is a polynomial of degree n. So we can write determinant of A minus lambda I as sort of a set of factors, lambda 1 minus lambda, lambda 2 minus lambda, so on and so forth. If we come back here, we can sort of see each of those types of forms in that characteristic polynomial. Some eigenvalues may appear more than once. So in this case, we can write, this form as lambda 1 minus lambda to the m1, lambda 2 minus lambda to the m2, down to lambda p minus lambda to the mp. That exponent is what we call the multiplicity of the eigenvalue lambda sub j. So again, if we come back over here, you could see that, like in example 2, we had a 2 here. So we would say that this eigenvalue, negative 2, appears with multiplicity 2. And then coming down, let's say here, again, we've got this mistake over here. I think this 2 is actually supposed to be up here. We go back to that video, you would see, I think that 2 is supposed to be there. So negative 2 is multiplicity 2, and here, this 2 is multiplicity 2. So, and the rest of these are multiplicity 1. If you had, bigger matrices, you could end up with eigenvalues that are multiplicity 3 or 5 or whatever, right? And it's just, the fact that we were only working with 2 by 2 and 3 by 3 matrices means we were a little bit limited. I guess we could have had a 3 by 3 matrix with an eigenvalue of multiplicity 3. But, in general, the multiplicity of these eigenvalues could be sort of as big as the matrix is. And then when it comes to the eigenspaces, so sort of looking at the dimension of the eigenspace, remember the eigenspace is going to be the span of the the eigenvectors, basically, right? So the null space of A minus lambda I. So the dimension of that, if lambda is a real eigenvalue of A with multiplicity m, it turns out that the dimension of that eigenspace is at least 1. Which hopefully makes sense, but at most the multiplicity of that eigenvalue. And if we go back to our examples, we would see that dimension of the eigenspace potentially being just 1 for those repeated eigenvalues, but for some of them it was 2. So at most 2. It could not be bigger than that. But it could be at most, the multiplicity. So the dimension of an eigenspace can never exceed the multiplicity of its eigenvalue. And then on to a key fact. So eigenvectors corresponding to distinct eigenvalues are always going to be linearly independent. And so when it comes to looking for a basis of eigenvectors for Rn, we get this proposition. If A is an n by n matrix, having n distinct real eigenvalues, I'll sort of highlight that because that's very key, important word here in this proposition. If we have n distinct real eigenvalues, then there is a basis of Rn consisting of eigenvectors of A, because each of those eigenvalues will have a eigenvector corresponding to it that for each one of these is linearly independent. So we're going to end up with n linearly independent vectors in Rn. Those will automatically be a basis for Rn, right? That is something we've seen earlier in this course, that if you have n linearly independent vectors in Rn, then they are going to form a basis of Rn. An important note, though, if an eigenvalue is repeated, there may or may not be enough eigenvectors to form a basis of Rn, so repeated eigenvalues require additional investigation. Some matrices with repeated eigenvalues have a basis consisting of eigenvectors, and specifically, I should say, a basis of Rn, while others do not. So if we go back to our examples, you could see that the first example, we have these two distinct eigenvalues. So yes, we get a basis of R2. In the second example, we had that repeated eigenvalue. And if you go back to, again, in the previous video, we explored this a bit further, the specific matrix. I don't even list that out here. But for that example, we found that the dimension of E sub minus 2 was 1. And so we would not have a basis of R2 consisting of eigenvectors here. The third example, we had complex. We're not going to explore that further in this class. For the fourth one, we move on to our 3 by 3 matrices. These are all distinct. And so, yes, this will form a basis of R3 since we have 3 distinct eigenvalues. The next one we have, again, I think this is correct. So we have the repeated -2. However, the dimension of E sub minus 2 was only 1. So if you go back to that last video, you would see that. And just so no one gets confused here, this is supposed to be up here. And then for that last example, we had the repeated eigenvalue of 2. And this time we went and we noticed that the dimension of E2 was actually 2. So yes, we could get a basis of R3 consisting of eigenvectors for this example. So looking ahead, if a matrix has n distinct real eigenvalues, then it has enough eigenvectors to form a basis. When it's repeated, two things can happen. We may still obtain a basis of eigenvectors, or we may not have enough eigenvectors to form a basis. This distinction will play a central role in the next section where we study diagonalization. So we're making this big fuss over, do we have a basis, do we not? And that is going to be kind of the key idea to understand when we look at is our matrix what we call diagonalizable? So can we diagonalize this particular matrix? So more on that to come.